All right. So, if you remember last class, I said the second half of this last chapter was where we take what we know about graphing, and last class we dangled it out the window, didn't completely let go of it yet, because the graphing was still pretty familiar. We still took our x and our y coordinates, we still graphed the points that were the xy ordered pair. It's just how we got x and y was a bit different. Today we let go. That sucker is out the window. Because today, it's going to be pretty different. Now, it's still going to relate to rectangular or Cartesian. We're still going to do that as part of this lesson, is how do I take polar and relate it to rectangular or Cartesian. But if we're really doing polar, it is a totally different system. Okay? And so, because it's so different, we're actually going to spend 3 lessons on this. So we're going to start out kind of slow today and just talk about what it means to be polar, how polar coordinates work, how a polar coordinate system works, and what that relationship is between polar and rectangular. Then on Wednesday, we'll take it the next step and actually look at, so then how do I graph a polar equation on a polar coordinate system. And then Friday, we'll finally get to that. So why do we do this with the conic sections? Because we'll do polar equations as conic sections. That'll be Friday. Which means next week, Tuesday will be quiz and review, and Thursday will be our final test.
Wow.
We got 5 days class left.
What?
Because then you've got 2 days the next week for
Review for fun?
What if you did no day, Monday's a holiday?
Yeah.
So what if Tuesday is day
But my grades are good.
Friday is day 1. How does work
Oh, yeah, so it's 2 days, whatever our 2 days are. Yeah. So Wednesday, Friday, sorry. Wednesday, Friday is review and test because we got Monday off. But it's the 2 days next week. Quiz review, test. Next week we got 2 days. Semester review stuff. We're done.
Oh, it's coming up.
So actual class, including the test, we have 5 days.
Fantastic.
All right, so let's get to it. Focus. Everybody's a little squirrely today, and I really can't talk over you. So, all right. So, introduction to this. So when you are asked to graph up to this point, you've always graphed in what's called the rectangular or Cartesian system, where your curve or your line is made up of the set of points that are represented by the ordered pair x comma y. And the x and the y represent the directed distances from the coordinate axes to the point. So when you say that I want to graph 2, 3, that 2 tells you 2 things. It first tells you the distance that you're going to go away from the y-axis. And then because it's positive, it tells you the direction that you have to go. You're going to go to the right instead of the left because it's positive. So that's what they mean there when they say it represents a directed distance. With the 3, a positive 3 is also a directed distance. The distance now is being measured from your x-axis because you're going up or down. And the positive means we'd have to go up. Okay? And so if you just take what we do when we graph, change it into words, and then translate it into math speak, that's what you get. That's what that first paragraph is. Okay, it's just the mathematical way of explaining what we normally do. But it says in this section you're going to study a different system, which is called the polar coordinate system. So, to form the polar coordinate system in the plane, we have to start by fixing a point O, which can still be considered the origin, just like the origin on a Cartesian system is, but it's also called the pole. Okay? And then from O, we need to construct an initial ray, which is called the polar axis. The polar axis is a lot like the positive x-axis in the Cartesian system. Then, for each point P in the plane, it can be assigned polar coordinates, which are r theta. Rather than xy, we go with r theta. And the two things that tells us, r tells us how far away from the origin we are to get to that point, and theta tells us what the angle of rotation was to get to that terminal side that the point is on. So when you look at this, even though the definition seems a little wonky and like, oh my gosh, I don't know what this is talking about, but if you just look at the picture for a second, you should see some familiarity here. Because this is really just based on trig. Right? We start with a point here at the origin. Our standard form always starts with the initial side being the positive x-axis. And then it's all about the angle of rotation to get to the terminal side. That's basically what polar is. It's about starting at this polar axis, rotating around to get to a terminal side, and then talking about how far away we are from the axis to get to this point we're interested in, and how much of an angle we had to rotate through. Okay? Now notice again, r and theta are both still called directed. Because again, it does make a difference whether it's going to be a positive or a negative. For theta, it's what we know from trig. Positive angle measures means we're going to be rotating counterclockwise around. If it's a negative angle measure, then that means we're going to rotate clockwise around. Okay? R can also be positive or negative. If I go a certain angle measure here, so that I get to this terminal side, a positive R means that I'm going that distance on that terminal side. From O to P, that's my R distance. But if I had a negative R value, then what that means is I would go the angle up here like this to get to the terminal side. But then if you imagine that this line continued down here, I would actually go the opposite direction to get to my point. So even though the angle put me here, the point actually goes this direction from it. That's a negative R value.
So
Yeah.
Sorry.
So if the angle is a negative angle and puts you down, and then the R value is positive, does that mean you're on the up path?
Nope. If it's positive, you are on the terminal side of that rotation. So if it's a negative angle and puts you down, and then you have a positive R, you go the distance that you need to go along that side.
Okay.
If it was a negative R, then you'd end up out here. because your terminal side actually ends up here, but your negative r puts you the other direction. Okay? Question? That was it? Okay. Any other questions that far? Come on.
So like basically, like now, the theta determines like the orientation of the axis, like the x and y, like what are the tensor amount?
If you were to superimpose x and y axes on this, they're still going to go through the origin. Right? So this O that we use as our point, as the pole, would be the same as the origin of an xy coordinate pair, coordinate plane. So we're rotating around as if our vertex is at the origin, just like we did with trig. Was that your question?
Yeah.
Okay, if not, clarify for me.
Yeah.
Okay? Any other questions thus far?
Can you re-explain the negative r and negative theta?
Oh, do I have any, like, just clear everything? Let me try this again. Okay, re-explain what?
When r and theta are negative.
Okay, so with theta, it's just like what we're used to with trig. Positive theta means we're going this way around, counterclockwise. Negative theta means we start at this polar axis and we rotate this way around, however far it tells us to go. Okay, so that's the difference between positive or negative theta. For positive or negative r, a positive r value means that if I go to this angle, so that this is my terminal side, my point is r units on that side. Okay? But this portion of a line really is a portion of a line, correct? So you can imagine that this line could extend in either direction that way, right? So if I get here as my terminal side, but I have a negative r, instead of going from 0 out this way to get to my point, I go from O this way
Oh, okay.
to get to my point. Okay, that's the negative r.
So there's two ways to write each point,
Seems that way, doesn't it?
or is there not?
But they're different.
'Cause if
We'll
you
get
make
to that in
it
just a second.
Positive, negative, and positive. Positive and negative.
We'll get to that in just a second.
Okay.
Yep. But that is what it's starting to look like, isn't it? Like there might be more than one way to represent a particular point, depending on what the angle is and whether it's positive or negative r, and yeah. So keep that in mind. We'll come back to that in a sec. Any other questions thus far? Okay, so actually to help us figure some of this stuff out, I want to transfer a couple of files to your TI Inspires. We'll definitely take a look at the one today. We might get to the other one today. If we don't get to it today, we'll get to it next class. So I want to just give them both to you today. So I think the easiest way that we did it in A block is if one person from each set of tables can come up, I will transfer the file to you from my computer. And then when you go back to your set of desks, take one of these connectors. Listen. When you are the person who's coming up, take one of these connector cables back with you to share it with the rest of your group. Remember when you're sharing, once you've plugged in to each other, you just have to go to the My Documents, find the document you're interested in, and then it's just menu 6. 6 should be your choice for send. Okay, if you have any issues, send the person up here. I'll try to give it to them from my computer instead, but this should work for the most part. Okay, so one person from each group, come on up.
Can we look on the computer? Another person's planner, because I forgot my pouch. Stuff in it. Was there a non? Still impressed to test. Also, is it okay if I use this cable right here?
I might have to change it. Not, I'll put it back in.
Alright, amigos.
The what? Sure. Oh, she has a buddy. Okay.
Okay, grab one of the short cords in there and share it with the rest of them.
Check you off the list.
Get it? Click OK.
Make sure that you transfer both. There's one that's called polar graphs and one called polar coordinates. Grab one of those.
Got it? Click OK.
Come on.
We're I swear to God, if you do. Oh, I got it. Like from the. Okay, I'm sorry, you're done. Got it?
Yeah, I was trying to send you stuff.
Around in the US, there's like
Yeah.
send you a file.
Short cord over there.
Got them both. Yeah. Think about it. Why do you have so many polar graphs and polar coordinates? You got it.
You were in the Holy class. The Holy stuff for months. The one did stuff stay on calculus.
Thank you very much. Press to test.
All right, so once you get them shared, then open up the polar coordinates file. Play around with the sliders on page 1.2 a little bit, and then answer these 3 questions on your notes.
Rat paper.
I'm coming.
I want to delete my press to test folder. I think that's how I will finally get rid of it.
You know what I'm with?
Yeah, sure.
Yeah. Is this supposed to be full gas?
And once you have the files shared, please return the cords back up here to the box.
In the area.
We'll go back to 0 after.
Nope. Oh boy.
Broke it. Nope.
It's in the area.
Well, we have to. Like,
Oh, mine's sorry. Perfectly at 720.
Okay. It's like so you can see it better. Right, I see. So why does the polar grid look the way it does? Yeah, I think so. Well, this way looks, instead of having graphs,
Oh boy.
On page 1.3, are we supposed to do anything?
We haven't.
No, in 1.3 something, Jonathan, 1.3 something has already been done.
Oh. Whoops, I went too far.
Well, also it has those 3 lines because it's based on trigonometry, so we can say that.
Oh,
You want to further modify.
You are the.
No, it says, certain other part.
Concrete ancestors.
Checo Fernando Escondido Tizón. They caught so many lines. So much.
The best lines.
Wait, Nate, did you only see it closing night?
Yeah.
You missed out.
There was a lot that was cut.
Is there another one? Yeah, this graph is
Wait, why
smaller
they
scale.
Wait, Jonathan, what do you mean they cut me?
Like, remember how Friday announcements, Mr. Kent was like, wow, that show was very racy. After that, like, they started cutting stuff left and right, like lines that were really, because, I don't know, administration was like, happy or something. I know. I probably shouldn't say because I don't know exactly why or who was the news was coming from to cut lines, but all I know is that like after a while, Mr. Doring was someone was telling Mr. Doring to cut lines.
Some of the best lines in tech that we always laughed at.
On the second day.
That's why you watch Open Mic. But I think we have one of her sing like tech.
All right, we got these 3 answered.
Is there another polar coordinate that represents symbol?
Ooh, there is another polar coordinate that represents the same point.
Actually, is there? It's positive, maybe there isn't. Actually, no, there is. So it'd be like, you can either have it be, so not 60, so 5. Well, what's this right here?
180
What degree value is it? 180
plus
is it plus 60, 240. So this is 240, and then you can say negative 3, right? 3 that way. Yeah, so 240 and negative 3. Another point. Is there another? Polar coordinate. Negative 3, negative.
All right, let's talk about this a little bit. Attention up here, please. So, obviously, one of the first differences you notice when it comes to graphing things with polar coordinates as opposed to Cartesian or rectangular coordinates is the graph you're graphing on. Looks very different. And so my first question is, why? Why does it look like this instead of like the little squares we're used to?
Because we're no longer graphing with just numbers, we're graphing with angle measures and numbers that are.
Okay, so why does this particular setup work better for that?
So this is negative 4.
Okay, so this degrees, or the angle measure, is what these radiating lines help us with. In this particular circle, each line is meant to represent 15 degrees, and you see that when you play around with the theta. You can see that my angle measure is changing by 15 degrees each time. Okay, on your paper, it's a little bit different, where your radiating lines out from the center are simply at the unit circle angles. And the reason for that is because when you are actually graphing a polar equation, you are probably going to start, at least, with relatively easy angles, which will be the angles from the unit circle, because you don't necessarily need a calculator for that. Now, 15 is not one that's on the unit circle, but 15 is the greatest common factor of all of the angles that are on the unit circle. And so if we go by 15s, then we hit all of the other ones, the 30, the 45, the 60, the 90, and so on and so on and so on. Okay? So that's what those radiating lines represent. What about the concentric circles? Why do we have those?
Because it represents the distance r.
Yeah. So it's going to represent your distance. If my r is a distance of 1, that means it should be a distance of 1 all the way around this center. And so we get a circle around that center that is 1 unit away. If I want a distance of 2, it would help if I had that distance of 2 all the way around. Well, that's what a circle is. It's all of the points that are equidistant from a center circle. So each of these circles just represents how many units out you are. And by making it a circle, then no matter what angle you're on, you can count exactly how many units out you're supposed to be. Okay? So the radiating lines represent theta, and then the circles actually represent r, because that tells you how far out you are by how many circles you're out. Okay? So I asked you to graph 360. So there's 60, 3 is the r, that just changes how far out we are. So you end up with something that looks like that. And if you graph that on your paper, then you should end up right there on what I have. This is a little bit different for you because of the lines and the way they are labeled. You do have them actually labeled on yours, but they're labeled in radians. So if you're given something in degrees, you just got to make that conversion so I can know which radian line you're on. Okay? And then from the center, you count out 3 circles. Boom, there's your point. Now the third question kind of gets back to what was mentioned a minute ago. Is there another way to write polar coordinates that would represent this same exact point?
Yes.
Give me an example.
-3 and 240 degrees.
Does that work? So 240 actually gets us all the way over here to that line. But because it's a -3 now, instead of going on that terminal side, we go the opposite direction, the 3 units. So yes, that is another representation. All right, what's another one?
3 -240.
3 -240.
Mm-hmm.
Does that work?
No.
Yeah.
That's -240, okay.
Yeah.
What's -240 at?
60
that
degrees.
Oh yeah.
Is it?
No, it should be -300.
Yeah.
Yeah, negative.
All right, my bad. My B.
First,
I was just guesstimating.
but yes,
So what should it be?
3 -300.
We can scratch off my mistake. I shall forever cower.
So yes, you can go negative for your angle. Just make sure you're going far enough. So -300 means starting here at this polar axis and going this way around. And then +3 means going out 3 units on that actual terminal side. Alright, that's gonna work. Any others?
Negative.
420.
Say again?
3, 420.
3, 420. Does that work?
There's a lot of possibilities.
I think
Or
infinite possibilities.
3, negative
Negative 3.
Negative 3, negative 120.
Yep.
So negative 120 would put us right there, but then go negative 3, so we have to go that direction. Yeah, so this is another major difference between polar and rectangular. In rectangular, if I give you an x, y coordinate, there's only one point that represents. And if I give you a point, there is only one way to represent it as an ordered pair. But when you start talking polar, one, because of the periodic nature, the fact that you can, well, I can go 60, I could go around one more time and come back, well, that's just 360 more, well, I could go around another time if I wanted to and come back, and the fact that you can go positive or negative, and you can use positive or negative r's, there's all kinds of different ways you can represent the same exact point. Now, there are times where that's nice, because it gives you some flexibility on how you write an ordered pair for a particular point. And there are other times where it's going to be a little bit frustrating because you're trying to actually find ordered pairs from a polar equation, and you realize that even though it looks like you came up with a different ordered pair, you end up plotting the exact same point you did 3 points ago. And that can sometimes be confusing, which gets you frustrated because you're like, well, where'd that point go? Because wasn't that this one? No, but that was that one. No, but no, oh yeah, they're both the same thing. Okay, so that's a really big difference between polar coordinate system and rectangular coordinate system, is the fact that a single point has multiple representations in the polar system. Whereas rectangular, there's only one way to represent it. Okay? All right, so just for a little extra practice, just do all 4 of these on one circle on your graph so you have enough graph space to deal with homework as well. Plot those 4 points on one of those circles from the graphs. All right, now take a second and think about where the point goes on my graph. It's a little bit different than what you have, so if you've got something like my graph, where's that point going to go? Okay, so what about this first one? If I've got 3 comma pi over 4, so now we're talking about radian angle measures rather than degree angle measures. If I start here at the polar axis, should I go clockwise or counterclockwise? How many lines?
2.
2. Right there? That one?
Yeah.
Okay, so this is pi over 4. Should I end up with a point that is on this terminal side or going the other way? On it, because it's a positive r, right? And how far away from 0 do I need to go? 3. So there's 1, 2, 3 circles out. That's the point I'm looking for. One thing that I find just a little bit deceptive with polar graphs is that my tendency is to want to do the rotation first and then figure out how far to go based on r. But notice that when you write the ordered pair, it's r first and then theta. Okay, so just be careful about that when you're actually writing coordinates for points. Make sure you're putting r first and then theta, even though your tendency is probably going to want to be to go theta first and then r when you graph. Okay. How about the next one? If I start here at polar, do I go clockwise or counterclockwise?
Clockwise.
Clockwise. How many lines?
3. No, 4.
4. 1, 2, 3, 4. Right there. Okay. So here's my negative pi over 3. Should my point be on that terminal side or going the other direction?
On.
On it, and how far from 0 should I be? From O should I be? 2. So 1, 2, right there. Okay. What about our next one? 2 comma 5 pi over 3. Ends up being the same, but did I get there the same way? No. In the green one, I went this way to get there. As the purple one, I'm going this way around to get there. But because 5 pi over 3 ends up being coterminal with negative pi over 3, and then because it's positive 2, a positive r in both cases, I end up at the exact same point. Right there. Okay. How about the fourth one? Negative 4 pi over 6. If I start at the polar axis, do I go clockwise or counterclockwise? Counterclockwise. How many lines?
2.
2. Am I going to have a point that's on this terminal side or the other direction?
Other direction.
Other direction. How far?
4.
4. So 1, 2, 3, 4. That's where my point should be. Okay, anyone have any questions about being able to do that? Because that's about a third of your assignment. If you can do that, you're going to be through that part really quick. All right?
Buenos.
Okay. So again, just reiterating this idea of multiple representations for the same point. If I start out at the point 3 comma negative 3 pi over 4, where is that?
3 lines out.
Clockwise, how far?
3 lines.
1, 2, 3.
No.
No.
And then another 1, 2, 3, 4, 5, 6. There.
There. Okay. Should I be on that terminal side or the other direction?
On it.
On it. And so 3 out, 1, 2, 3. That's the point I'm talking about.
Yay.
Okay. Now it's asking for 3 additional polar representations of this point, But notice it's giving you a limit to what angle you can use. So you have to keep your theta between negative 2 pi and positive 2 pi, but there should be at least 3 more ways to represent that same point. So we're starting with negative 3 pi over 4.
Pi over 4 negative 3?
Well, negative 3 pi.
Oh, yeah.
Say again?
Negative 3 pi over 4.
That work?
Yes.
Pi over 4 puts me here. Negative 3 sends me the other direction. Okay, another one.
5 pi, no, 3, comma, 5 pi. Yes. Tricky.
Is that gonna work?
Yep.
Yeah.
So 5 pi over 4 is this way around to there, and then 3 would put me right on that terminal side.
Negative 3, 7 pi over 4.
Is it?
No.
Negative 3.
Yeah, it's
7 pi.
negative, yeah.
Negative 3.
7 pi over 4. 7 pi over 4.
Wait.
Oh
No.
no.
It's gonna go the other quarter 2.
Oh, wait. So
Negative 3.
That'd be quarter 2. I don't think there's another. Yeah, there's no more. I think we're done. Yeah.
No, there's gotta be more. Okay.
Negative.
Negative 7 pi over 4, negative 3.
Negative? No.
Negative
But
3.
3, 13
7,
pi over 4.
Negative 7 pi over 4.
We're done.
Yeah. Negative 7 pi over 4, negative 3, negative 7 pi over 4.
Oh yeah.
Like I said,
yeah.
because you go all the way around and then you go back.
I asked you 3 times, Dennis. I never heard the negative, so you gotta speak up, boy.
Yeah, you said 7.
If you said positive 7 pi over 4, that doesn't work. Because positive takes you this way around, and then negative puts you here. Right? But negative works. Because negative 7 pi over 4 puts me here, and then negative 3 puts me down here. Okay? Does 13 pi over 4 work?
No, but it's not within the limit.
Exactly. You gotta stay within negative 2 pi to positive 2 pi. So you gotta be careful if they give you that kind of restriction that you stay within it, otherwise your possibility is not gonna count. Okay, so these would be the 3 you'd be looking for within that range. Okay, go back to your calculators for a second and go to 1.3. So if I had not told you anything about polar coordinates yet, and the very first thing I showed you in this lesson was this screen, tell me what you already know about this screen.
With the right triangle.
Okay?
States the obvious.
Certainly appears to be that way.
So it's like
Say again, Nicole?
unit circle. It looks like unit circle.
Okay, we've seen something like this when we were talking about unit circle.
It has a point at the origin.
So we've got one vertex here at the origin.
The one.
We've
line
got one
that-
vertex out here, which they're calling the
X,
point
Y.
x comma y.
And then that one's
And one-
cosine.
Cosine sine.
So what?
Cosine
That that would be cosine
Cosine
theta.
theta.
Yeah.
Sine
Cosine theta.
Sine
Sine.
theta.
Wait.
But what is cosine theta?
X.
Oh,
Is it?
That's if
We
you're
saw
looking at
this
it
in
on a square
relationship
grid.
to a unit circle, but is this one actually a unit circle?
Oh no.
So it's r comma theta. It's not. Y is equal to theta.
No.
What? No.
It's what?
X over.
What's sine going to be equal to?
Y over.
Can you tell me anything else?
Well, so it's cos. Oh, we're not cosine. We can figure out tangent.
What would tangent be? Tangent would be Pythagorean?
No, it's opposite over. So sine over cosine.
Y
over y.
Yeah, there we go.
So what about Pythagorean?
X squared plus y squared is r squared.
And where else have we seen that?
circles.
Equation of a circle.
That's right.
That's how we get all of these xy points to make a circle, is we're really just using the Pythagorean of that setup. Okay? So, if all I did was show you this picture, we already know a lot about this based on what we know from trig. Okay? We're going to use these relationships to help us convert back and forth between what's polar and what's rectangular. Because the xy is back into rectangular mode, right? So when we start talking about the point as xy, and we know we have these relationships as it relates to trig, since trig represents using angle measures, thetas, we're dipping our toe into polar land, right? Like, okay, so that there's that connection there. And r is the same r. The r that we were using in trigonometry is that distance from the origin or pole out to the point we're interested in. It's the same exact r as what r is in polar. Okay? And so using those relationships, we can then come up with an equation for x. How do I get x by itself? Multiply both sides by r. X is going to equal r times cosine theta. How do I get y by itself? Tangent doesn't have an r in it, and we've got both x and y, so we're not really trying to get those by itself, so we just kind of leave that as is. And here we got everything taken care of. We got x, we got y, we got r. And so what that leads us to is a way to convert back and forth. So if you are given polar coordinates, r comma theta, and you want to change it into what would be the coordinates of that point if it was on a rectangular system, then you can use x would have to equal r times the cosine of your theta, and y would have to equal r times the sine of your theta. So that r and that theta you're given in your polar coordinates, you can use those to come up with what the x coordinate and what the y coordinate would have to be based on those relationships we already knew. So this isn't magic. I didn't pull this out of thin air. All right, we're just reworking what we already know. If I want to go the other direction, by the way, this is wrong, so don't write that one down. If I want to go the other direction and start with rectangular and change it to polar, I can use the fact that the tangent of theta equals y over x, because that now uses both the rectangular coordinates, and then, since I know tangent of theta has to equal that, I should be able to take inverse tangent of whatever that is to find out what theta is. Right? And for my r value then, I can use my Pythagorean or my circle equation, however you want to think of it. Again, it has both x and y in it. So I put in my x coordinate, I put in my y coordinate, and I know r squared has to equal that. And so I can figure out what the r is that's supposed to be in my polar coordinate. So those relationships we already knew, we can now use to go back and forth between polar and rectangular. Make sense? Everybody got that wants it? Okay, so let's do it. If I give you the polar coordinates of root 3 comma pi over 6, what would be the rectangular coordinates? At the same point. And remember, this is always assuming that the origin in polar and the origin in rectangular are matching up. So your x-axis is going through the 0 pi line, and your y-axis is going through the pi over 2, 3 pi over 2 line. How are we going to find x?
R times cosine pi over 6.
What's my r?
The square root of 3.
What's cosine of pi over 6?
Square root of 3.
So what's root 3 times root 3? Where's my x coordinate?
Yay.
And again, you're seeing that connection between the x and the cosine, right? For x, it's going to be r times cosine. For y, it's going to be
R times sine.
r times sine. So still working with root 3, but now we're taking the sine of pi over 6. What is the sine of pi over 6? So the actual ordered pair in rectangular coordinates
Is 3 over 2, square root of 3 over 2.
Root 3 over
So if you took your polar circular graph thing and you had a rectangular graph with x and y coordinates that had the same scale in terms of units. So the distance from your pole to your first circle is 1 unit. So when you overlay the rectangular, that distance from origin to 1 unit has to match up. Okay, so if all that matches up, the point that would be at root 3 comma pi over 6 on your polar is going to be at the point 3 halves comma square root of 3 over 2 on the rectangular. How about the next one? Convert 2 comma pi. If you don't have it by now, you're doing it the hard way. Negative 2, 0. Because think about where that is. Your angle is pi. You're on an axis, right?
Oh.
If your angle is pi, and then you went 2 units, you're right there on the axis.
I was accidentally trying to convert into.
So, pay attention to that. Question?
Just one guy.
Never mind. I get it.
Okay. But pay attention to that, because if you get angles that put you right on the x or the y axis, you don't really need to go through the computation, right? You can just kind of go, oh, well that means that I'd be this many units on that axis and it's this point. So if you get a pi over 2, a pi, a 3 pi over 2, a 2 pi, anything like that that puts you on the axis, logic it out. Okay? But if you get anything else, any other angle that doesn't put you right on an axis, put you somewhere in one of the quadrants, then you're going to need to probably work it out. Okay? So negative 2 comma 0 would be our coordinates there. How about the other way? Now I'm giving you the rectangular coordinates, and you want to come up with what the polar coordinates are. So if I'm at negative 1, positive 1,
Could. Oh, there could be multiple answers.
so let's start with theta. How do I find theta?
Tangent theta is equal to y over x, which is just negative 1.
Okay. So what is theta going to be?
It's either negative pi over 4 or something pi over 4. 3 pi over 4. 3 pi over 4, 7 pi over 4, negative pi over 4, negative 5 pi over 4.
There we go.
There's a range.
Inverse trig.
Oh.
restriction on your range.
There's range, but
Now, having said that,
Andy, come on, man.
you could then take negative pi over 4, which is the answer. Right? As far as it being an inverse trig function, the only single answer you can get for output from any one given input is negative pi over 4. But then you can use that to come up with what some of the other possibilities might be. Okay, but as far as answering this and solving this equation, your only answer is negative pi over 4. Okay, because we're still dealing with an inverse trig function. We still have a restricted range. We got to live with that range. Just because it's not that lesson anymore doesn't mean we get to throw it out the window. Okay? Now, what about r? How am I going to figure out the r value?
R squared is equal to x squared plus y squared square root of 2 squared. Maybe. No, square root of 2.
Thank you. Now, the reason I took a deep breath and waited for you to give me plus or minus square root of 2 is because now, when we go to figure out what this really should be, we've got options. We can go positive or negative for r to make this work. And so you want to think for a second, like where actually is negative 1, 1? What quadrant are we talking about? Second, negative 1, positive 1. We're talking about a point that's right about there. Okay, so if I really go with a negative pi over 4, if I decide to go with that angle, then it's going to take a negative square root of 2 to get over to that point. Which is fine because technically, when I take the square root of both sides, I can use positive or negative for my r value. So one possibility is that we go with a negative root 2 and a negative pi over 4. But then as we've already talked about, that's not the only possibility. So you can come up with other things like 3 pi over 4, positive root 2. Or 7 pi over 4, negative root 2. Or whatever from there. Okay? But, and here's the big single T but. Not the double T but. We don't need to talk about those. Single T but. You are going to need to show me that you are setting up this equation to find theta. And if you do inverse tangent and tell me anything other than what the restricted range allows, you are going to lose points. So as the solution, you need to tell me the correct theta. What you then do with that to come up with an ordered pair is okay. Like if you want to then take that and say, well, that's really the same as 7 pi over 4, okay. But you got to show me this first. You got to show me where you came up with that number to mess with. Okay? Same thing here. You're going to have to show me that you're getting r from this Pythagorean or circle equation. And if you only give me the positive square root here and then come up with some negative over there, I'm going to call you on it. So make sure you're giving me plus or minus here. That way you have options over here on how to set this up. Okay? All right, last quick thing. Because we now know how to convert coordinates back and forth, it also gives us an ability to convert equations back and forth. Now, there are ways to do this, but based on time and based on what I would really like to accomplish this lesson, I kind of put it here in case we had time, but I'm not really worried about this, so I actually took these problems back off of the homework. So the going from polar to rectangular is a little bit more tricky. It's not quite as straightforward. You have to be a little bit creative about how you come up with those. So I'm not so worried about that right now. But you should be able to do this. You should be able to take a rectangular xy equation and change it into a polar equation. Any ideas how?
You can substitute x and y for what we talked about before.
Yeah, so what would I substitute y for?
Angle, theta.
Well, our cosine.
Cos theta. Sine theta.
Oh, sine. R sine theta.
Is equal to r
And what would we,
r cosine theta squared. Squared.
so this is going to become r squared and cosine squared. Now, if you really want to get this into a polar equations generally go opposite of rectangular anyway, because rectangular is usually x comma y, but our equations are usually all y equals something. With polar, it's the other way. We usually go r comma theta, but our equations are always r equals something. Okay? So if I try to get r by itself,
Divided by r. Yeah. Divide sine.
and then what?
Divide cosine.
That's not very good. Let me do that again. Ooh, that was big. This was r cosine squared. Okay, so cosine squared. So r is going to equal what? What's the most simplified way we could write that? So if I go with a tangent theta, then what's left?
Tangent over cosine.
Oh, tangent times cosine. One over cosine.
Take that one more step.
Tangent.
One over. One over. Secant.
Yeah, secant.
that would be your polar equation. Okay, because we're splitting up this cosine into two separate ones, so we're putting one cosine under sine to get tangent. That leaves us with 1 over another cosine, and that's secant. So yes, I heard, it was good. I heard some thinking going on there. Can we divide both sides by that r? Yes, we can, because r just represents a coordinate, and so it's allowed. You can divide both sides by r to simplify it down. Okay, so there are a couple of problems like this. They're going to ask you to do this rectangular to polar conversion. Most of your problems are going to be plot the point, come up with other ways to represent the point, convert polar coordinates to rectangular, convert rectangular coordinates to polar, and then there's just a couple that are like this. Okay?
Sounds good.
If you are smart about it, and maybe double up on a few of the ones you're asked to plot, you should be able to get everything on the sheet that I gave you. With what's left, you've got 6 on the front, 6 on the back. You might need to double up a couple places, but you should be able to fit it all on without it getting too messy. But if you do need another one, I put the link to this graph paper on Canvas. But I think you could probably get it all on this sheet if you were smart about it. So. This will be good for Wednesday. Wednesday we'll talk a little bit more about that other polar graphs file that I gave you and about how to actually graph equations. Also, heads up, Wednesday, we do not have chapel. So you come here as if it was a Monday, Tuesday, Thursday, Friday schedule. You come right after lunch. Okay? Chapel is Thursday during the office hours time this week. Because Wednesday is the teacher appreciation luncheon, and so with all that going on, it was easier to not do chapel on Wednesday. There's some other stuff going on too. Next quiz will be, what is it, Wednesday? Next Wednesday. Because we don't have school Monday. Oh, that's Tuesday's day 2. So Wednesday would be. Then you'll have to wait for some motion.
It's funny though, I don't get it.
I'll try to get that updated in the next day or 2 so you guys can see that.
Whenever just did live, like the last week.
Alright, I'll see you Wednesday.
Like that large. You never laugh. You guys never laugh. So